Hi, everyone. Thank you again for joining us for the NVMe Power Governance in the Age of AI Power Limit Measurement and Threshold in NVMe 2.3 Technology webinar. For our webinar today, we have Ivan Lobachev from Solidigm. With that, Ivan, I'll go ahead and hand it off to you to kick off the webinar.
Cool, thank you. So welcome everybody. Today we'll be covering the feature 2.3, which was introduced in NVMe revision 2.3 of the spec. We'll be covering what it does, the thought process behind it, and how it complements the baseline that was previously defined in revisions 2.1 and 2.2. We'll also be touching on some of the other power-related features that are available. That you could implement should you so choose as optional capabilities, but they are absolutely not required for 23 hex to be working. I will be aiming to keep the presentation in the 20-25 minute range, but Nolan here will keep me honest. So with that, let's go ahead and jump right in. As Nolan mentioned, my name is Ivan Lobachev. I'm a technical marketing engineer for Solidigm, and I also work on the PCIe and NVMe specs on behalf of my company. So for the agenda today, we'll be covering kind of like the problem statement that was present, the mechanics of the new feature. We'll then touch base on some of the other power-related features that are available to you. Some additional context that kind of defines the implementation, and then some of the key takeaways that I would probably want folks to walk away from this presentation with. So as many of you know, client platforms tend to have power envelopes that change at runtime. That means things like, are you battery powered? Are you AC powered? There's thermal headroom that's available to you. There's user-selected power modes. NVMe 2.1 and 2.2 model does let a host pick a power state by index. And the power state descriptor table in Identify Controller does expose a wattage for each of those states. So technically the BIOS could, in theory, read it, walk the PSDs, and pick the right index for the target watt budget itself, just like what's currently done in the data center host drivers. However, the reason that that approach would be less attractive in the context of a client BIOS is a bit more utilitarian than architectural. BIOS would, in that case, also have to renumber the autonomous power state transitions entries that point to the now undesired state. So it would have to accept the fact that the OS will still see the unfiltered PSD table when it reads identify. It would then also have to accept the fact that set features with safe persists a specific power state index, which a firmware update reordering the PSDs could actually invalidate. And then it would also have to repeat this for every controller in a multi-controller setup. The feature that's introduced in NVMe 2.3, which is 23 hex power limit config, is a device side primitive that would basically hand all of the bookkeeping to the controller with a single watt level command. This presentation is fairly acronym heavy. I will do my best to explain them as I go through the slides. However, Nolan should have posted a glossary into the chat window that I prepared. Feel free to refer to it throughout the presentation just to make everyone's life a little bit easier. So let's talk a little bit about the history here, which is how did the power selection work in the previous revisions of the spec? As this is kind of what we're building upon. So both in NVMe 2.1 and 2.2, the host would usually pick the state by writing a 5-bit index into the set features register. The PSDs are then baked into Identify, and they do not change. This is a somewhat important point that I would like to anchor here. The only quote-unquote enforcement primitive that NVMe ever had is the statement that the device shall not exceed the maximum power in watts of its current operational state. That rule has been there since 2.1 and 2.2, and it's obviously unchanged in 2.3. So feature 23 hex does not technically add a new enforcement privilege. What it does is it changes the selection mechanism from an index-based to a watt-based without the extra steps on the host side. Now, it's important to keep the distinction in mind through the rest of this talk. Let's talk a little bit about the mechanics of this new feature. So I would potentially argue that this is one of the more important slides in the session. Feature 23 hex sets a watt level cap for the device, and then the device responds by reshaping the power state descriptor set, renumbering the APST in tandem, and then reconciling power management defaults and updating the NPSS, or the number of power states supported, atomically, before the change becomes visible in identify. This is quite important because the cap is not an enforcement target, because we're still kind of operating on the shall not exceed maximum power rule. What it does is the device now runs at the highest non-prohibited power state descriptor's maximum power, which is at or below the cap that was set. So for example, if you set a 16-watt cap on a hypothetical example drive that is currently used in the spec, actually, you would have a drive that's running at 15 watts, because that is the maximum power state defined by, that's the maximum power defined by the power state of that device, not 16 watts as the cap defined by the host. As mentioned previously, the value of the feature would be basically, all the bookkeeping for it would be done atomically by the device itself. The PSD watts have been visible by the host we identified previously, but now all of the reshaping, all of the renumbering of the PSTs, all of the persisting as a watt cap and adjacent information is basically handled by the device, which would have previously caused the host some headaches to do manually on its end in some context. Let's talk a little bit how this process works. I've tried to break it up into 8 steps, and I'll pretend that I didn't make it 8 just so that it fits nicely on the slide. Basically, step 1 is we want to retain a clean copy of the originals. It's going to be saved in the RPSD set, the removed power state descriptor. It will make the restoration deterministic later, and we'll talk about that in a bit, why that's important. And then steps 2 through 6 essentially perform the actions necessary to perform the reshaping, right? Like we prohibit the states that exceed the cap, we remove them from our PSD tables, we shift the PSDs around, we shift the APSTs, and we make sure that we have like our PSD tables looking clean. Now, in step 7, we reconcile the power management. So steps 7 and 8 basically propagate the renumbering into the power management feature values, as well as the APSD ITPS fields, such that the host now sees a coherent host compaction view of Identify, which would allow it to operate much more cleanly. I do tend to include sections of the spec that are referenced in each slide if somebody wants to refer to them later when they're rewatching the recording. I think it would be helpful to maybe work through an example as a means to better understand how the feature would work. So here we have on the left, we have basically a table representing the power states of a drive before a cap is applied. Do notice that there's a duplicate 18-watt power state. So the host would then issue a set feature command with the power limit value of 1600 and a power limit scale of 1 binary, which would essentially translate to a 16-watt cap. The device, as a result of that, would prohibit power states 0, 1, and 2 because their maximum power values exceed 16 watts. And then the remaining 4 states are renumbered, and the NPSS would then go from 6 to 3. The default would remap to the new power state 0, which is 15 watts. And as mentioned previously, notice that even though our cap is 16 watts, our operational wattage will actually be 15, as that's what the power state leverages. Now, obviously, 23 hex doesn't actually unlock a new operational point. What it does is it kind of limits our menu and our selection to what makes sense. And then the maximum limited power as well as maximum limited power scale still reports 25 watts. And this is so that the host would always know what the device could do should it go uncapped. And this actually brings us to our next point, right? Like the restoration of the power states using this feature. If you wanted, for example, the full performance that the drive has, and you're able to handle it now, you could do the restoration, and it is deterministic since you capped all of the originals via the RPSD set that we mentioned earlier. Now, raising the cap doesn't accumulate any rounding error, since all it does is it just rewrites the values from the baseline that you already saved. It's important to note that the power limit value equals 0, or PLV equals 0, is a special case that essentially sets the cap greater than everything. So what it does is it would restore your table to whatever the maximum power the device can support. And last but not least, if you set the power limit to be something invalid, right? Something that device doesn't support, meaning, for example, you have no operational states available, you would get an error 3E hex, which stands for invalid power limit. It would essentially fire when the host asks for a cap that no operational state can satisfy. And for those who may be wondering, an operational state is defined as the NOPS bit being 0 or 1. Let's talk a little bit more about some of the other power-related features I mentioned previously that are available in NVMe. One of them is the 25 hex, which is the power management option. It is an optional standalone feature. It has been available since revision 2.1. Since it's not really tied to feature 23 hex, you could absolutely enable and implement it independently, regardless of whether or not you do any other power-related feature, 23 hex included. You would enable it by setting ACT equal to 1, and you would essentially stop your recordings by setting it to 0, fairly easy operation. The stop measurement timing also gives you a built-in auto stop. I guess there's two small quick features that I probably want to call out, and that is that the power histogram bin size is capped at 250 milliwatts. And the feature itself is technically not savable, but the current value does persist across power cycles, as you can see in figure 403 of the spec, should you ever go back to check it. This is like a pretty nifty feature that a designer could choose to leverage should they want a device side power telemetry enabled. Another feature that has also been available for a fairly long time, again, since like 2.1 or earlier, is feature 24 hex, which is the power threshold. Just like 25, you can implement this by itself if you wanted to. It does not require you to implement any power-related feature. So the EPT essentially enables you to do one-shot events, meaning you would measure power when would kick off the measurement when the measured power would cross a threshold. And then an ASIC event would fire and the device would clear the EBT. The host would then proceed to rearm the event handler. And this is simply done just to avoid alert storms. Those of you who deal with firmware would probably know that those can be quite a headache. The PMTS would then basically select, the PMTS selects which power source to watch. This helps with having event-driven power awareness rather than polling it. Can be helpful in a number of different implementation scenarios depending on your needs. The last little tidbit of features is the MBW, or the maximum bandwidth field, in the PSD. So this has been added in revision 2.3. And what it does is it tells the host the highest sequential read bandwidth attainable in the state when the commands are maximum data transfer size length. And the queue depth is the optimal aggregated queue depth from identifier. Now, when you combine that with maximum power, each power state becomes a watts and megabytes per second point. For client platforms, that's quite useful for the OS power policy, which could basically use it to make the informed cap decisions when it switches various power modes.
Yes.
So we covered the spec mechanics. Let's talk a little bit about some background on where 23 power limit config actually fits. And I'll probably touch base a little on where it probably won't make too much sense. So the title of the slide is misleading. It fits the client space problem mostly because of a few design choices that you would usually make there, such as variable platform envelopes. You have power budgets that may actually change at runtime, and you have a number of other both physical and electrical limitations present. It allows you for an atomic reshaping, which means the device would perform all of the bookkeeping for the power, including things like APST, power management defaults, as well as the NPSS, which is helpful to the OS for the coherent view of the post cap of identifier. It provides you with a pre-OS binding, which means you could apply this cap and save it before the OS Power Manager ever comes up. And lastly, it's just like before, it's mostly a guideline, so it's not exactly an enforcement target. We still rely heavily on the maximum power rule to perform the actual quote-unquote enforcement. But the power management and the APST features, they still work with the existing client power management code path to make sure that that flow is operating as usual with the renumbered table. I think at this point we're actually going to jump a little bit away from NVMe and into where it fits in the larger picture. So NVMe obviously needs a physical layer to write on, and that in most cases is PCIe, or I should say in most cases, in a lot of cases, it's PCIe. In case of client context, we're going to be using 5.0 as an example, and since a heavily prevalent form factor for client devices, laptops in particular, tends to be M.2, I'll be using that as an example here. And essentially each of these has its own way of helping to make sure that we maintain a certain level of power limit or power governance. PCIe, for example, defines something called a set slot power limit at the transport layer. And it uses the same TLP encoding across all the PCIe revisions. The M.2 spec actually defines the absolute electrical envelope that's categorized by the connector key, the M key, which the NVMe SSDs typically use, allows for up to 16.5 watts for normal operation and 23 watts for peak. However, realistically speaking, just due to things like thermals and potentially even things like excessive power draw, most laptops do tend to limit it to single-digit watts. And so this actually brings us back to the power limit config, which would sit on top of those layers at runtime and provide an adjustable cap that the BIOS or the embedded controller actually on the device would actually drive. So with that said, I would say that these are the typical gotchas for client SSD firmware teams and BIOS and or OS integrators adopting feature 23 hex that you'd probably be good to be mindful of. The first one on the list is identify caching is probably the biggest behavioral shift. You probably shouldn't cache it anymore. Primarily because the APST must move in tandem with the PSDs. So having stale information there could cause you some fun times. The validation metrics becomes non-trivially larger than the static model we had before. And you still need to coexist with the NVMe 2.2 hosts. So that's going to be interesting. And then lastly, the error path for the maximum limited power and the maximum limited power scale reporting. Those must be exact because since that's the host only view into the original capability, when the when we introduce the cap and while it's active, that's the only way the host can know what the drive is actually capable of. All right, let's recap kind of what we talked about here. So feature 23 hex, which is the power limit config. You get two companions that are optional, choose one, choose none kind of deal. So 23 gives you the watt level based selector for your maximum power. We've covered in fair bit of deal in this presentation. 25, which is power measurement, and 24, which is power threshold, are additional power telemetry options available to you since 2.1. So if you're adopting 2.3, you'll likely already have a version of that implemented somewhere in your code base. They do not depend on 23 hex and vice versa. So, and lastly, the designer can basically choose to enable any and all combinations or none of them, depending on what you feel the platform requires. All right, so we're basically at the end of the presentation, and as mentioned, we're going to go over a few takeaways that I would probably want folks to walk away from this talk with. The first one is the power limit config is a selection enhancement. It's not an enforcement mechanism. The second is I would consider it to be much better suited for client applications. The third is the power state descriptor compaction process is probably something that should obtain a little more of your focus if you're implementing this feature. And then lastly, it sits on existing other layers without altering them, which is a default, obviously, but it's important to consider kind of your system holistically. And lastly, you do have other power-related telemetry features available to you, should you choose to add them. I think we're good to open for questions.
Awesome.
And I managed to keep it under 25 minutes, which is great.
Awesome. Thank you, Ivan. Well, now we'll go ahead and dive into the Q&A. So if any of our audience members have any questions, please post these in the Q&A chat and we'll help to respond to these. Looks like we've already got a couple here. So I'll go ahead and dive in. The first question is for feature 25H, does this set a window in which a power measurement device records actual power, such as a Quark device or current probe/scope, or is this a way to capture PMIC settings to calculate power?
Okay, so I'm going to try to rephrase the question first. Feel free to call me out if I botched it. Does the 23 hex alter how we measure power using the other features in NVMe? I think would be a simpler way of asking that question. I know you added the context of scopes and other devices, but I think in the grand scheme of things, the answer would be those are two independent avenues. 23 hex very specifically targets what power state you operate in. It is very tangential to the power telemetry that you were mentioning. Those would be better suited to be achieved by the other power telemetry features we talked about, such as 24 and 25 hex, depending on how power conscious you are, what you're trying to achieve. Does that answer the question?
Let us know if there's any follow-up to that question. But the next question that we received is, you mentioned the other power management capabilities. Were these available in the specification before NVMe 2.3?
Yes, so that's actually a great question. We touched base on this a little, but 24 and 25 have been available since at least revision 2.1. So those have been around for a little while. They're actually leveraged by data center flows today. So I'd say the only other addition, as I mentioned, in 2.3, and that's mostly to complement the 23 hex, is the maximum bandwidth field in the PSD.
Awesome. And then going back to that first question, it looks like they were talking about 25H. Is there any additional context, Ivan, that you'd like to provide there, or?
Oh, no, no. So 25 hex, like nothing changed on that in 2.3. So if you implemented that previously, that should operate as usual.
Okay,
There's no impact.
great. Awesome. And then one more question looks like, can we implement, or can these features be implemented via NVMe MI?
Ooh, that's a great question. I will have to be honest. I'm a little shaky on the MI implementation. I think, but if you fire off this into the technical working group email, I either myself or some of my colleagues will be happy to get back to you on that.
Awesome. Great. Well, that looks like the last question that we have for today. So thank you to you, Ivan, for presenting, and thank you to everyone for joining today's webinar. If you'd like, the webinar video will be available to view on the NVMe Express YouTube channel, and we'll also be uploading these slides to download on the NVMe Express website. So thank you everyone for joining. Have a great rest of your day.
Thank you.